Hi, and welcome to S for Science. And do you see that red spot? Because the same number of people live there as those who live in the blue zones combined. If you're watching this video, it is very likely that you're one of the 8 billion people who live on this planet. In a certain country, in a certain town or city, you're probably one of those 8 billion people. However, 7 octillion. 7 octillion is the number of atoms that you have in your body, which is a greater number than the number of stars in the observable universe. Atoms. What are you made of? In the same way as, for example, with a bag of chips, it is possible to make an ingredient list of what your body is made of. As you hear, we're nothing more than the combination of many atoms of different elements, ordered in a very specific way that forms you. More than half of your body, for example, is nothing more than oxygen. Yes, that gas that we inhale, followed by carbon, of which coal is made of. Occupying the third place, we have hydrogen, a highly flammable gas. And you even have a little bit of gold and a little bit of uranium, a 0.0000013%. But that's fine. It is normal to have a little bit of radioactive elements in your body. In fact, for example, bananas contain a radioactive isotope of potassium. It's not much, but if you ate 274 bananas a day for 7 years, you would die from radiation. The same thing would happen if you ate 10 million bananas in one day. Although before dying from radiation, you would die from eating too much. The thing is that almost everything that we eat have a complex list of ingredients. Strawberries, lemons, eggs, kiwis. Food. If we think about it, the atoms of our body come directly from what we eat. So maybe we're not really from the place where we were born or where we live, but from where the food that we eat comes from. Right? A few decades ago, the world situation was very different. The food that we consumed was very local, with international food trade being quite scarce. So, if we are what we eat, before we could affirm that we were actually from the place where we lived, since all the food was produced close to our house. But this is no longer the case. It's different. Yesterday, I ate tuna from the Atlantic, avocado from Mexico, and kiwi from New Zealand. And I live in a Mediterranean city. So, where am I from? Where are you from? Well, it is impossible to find an exact answer, more than anything because we all eat things that come from different places. The only sure thing is that almost all countries in the world export and import food, so it's probably correct to say that you are from all over the world. Obviously, sure, some part of what we eat is cultivated or made of atoms that are from the place where you live, or at least very close. But it is undeniable that there are many atoms that come from other countries, from other cities, from other continents, and from various places of the earth. So you're really not from a country or from a certain area of the earth. You are from the whole earth. Beautiful. No, it's not, because it's false. Our planet is usually considered a closed system. This means that the earth is an ecosystem that doesn't receive, apart from energy, nothing from outside. A system that is completely closed or isolated. But this is not true, because some parts of the world are more connected to outer space than with the actual terrestrial mantle. Because oddly enough, our planet gains in weight every year 2 Titanics, that is 80,000 tons of space dust that reach our planet every year, in the form of micrometeorites that can be found anywhere on the Earth. And also, they are very easy to collect from the roof of your house. But the thing is that 2 Titanics per year are too many atoms. Atoms that become part of our ecosystem, part of us, part of you. On the other hand, part of the material that we consider from the Earth or terrestrial is lost every year into space, non-stop. We humans have this habit of sending a lot of rockets and ships into space. Every year, dozens of space missions take off that leave the Earth to never return. Could this affect to a significant loss in planetary mass? We just have to do the calculations. In the year 2016, for example, 80 space launches were made, each of them weighing approximately 500 tons. So we sent to space 40,000 tons of terrestrial material. One Titanic. But the thing is that we have left out a very important concept in rocket science. Because we need to remember that to reach and remain in space, an object needs to reach a minimum speed of about 25,000 kilometers per hour in the case of the Earth. And that requires a lot of fuel. That's why going to space is so expensive. Of the mass that we see take off in a rocket launch, only a very small fraction reaches space. The remaining fuels and fuselages are left behind. Sometimes we drop them in the sea, and others we recover to use again, as it was done with the Space Shuttle, or as the SpaceX does now with its amazing Falcon 9. So, no, the matter that humans send to space every year is quite negligible when making these calculations. So, can we affirm that effectively the Earth gains in weight 2 Titanics per year? Well, unfortunately, no. The Earth loses about 100,000 tons of hydrogen and helium per year due to atmospheric escape, which we already explained in another video. But it simply is due to how light these elements are. This is what allows them to quickly reach the escape velocity of the Earth when they receive a little energy. Is this a problem? Well, not in the long run, because before the atmosphere runs out, or we can notice a significant change in the atmospheric pressure, the sun would have already swallowed us. Although it is a problem for helium, a gas increasingly valuable and increasingly scarce. So yes, this planet is losing mass. While every second that passes, 2.5 kilograms of space dust fall to the Earth, we lose 3 kilograms in the atmosphere. So the result is negative. But in the end, we continue to receive a daily shower of cosmic dust. And for what we're interested in this video, it's more than enough. Because it means that we're not only from the Earth. You're a bit Martian, for example, given that every few decades we receive from the red planet small pieces that were expelled from meteorite impacts. This implies that you have in your body millions of atoms that a few decades ago were part of Mars. Yes, you're from the Earth, but you're also a little bit Martian. But that's not all, because you're also a bit interstellar. There are estimates which say that around 5 billion of the water molecules that are now in your body came to the Earth in the last century from interstellar space. Obviously, these numbers are not exact, but their orders of magnitude are. What I mean by this is that it's impossible to determine how many Mars atoms you have, but we can make a pretty good estimate, because we may confuse 10 with 12, but we're not confusing 10 with 1,000, for example. But this is the interesting thing. You not only have atoms from the other side of the world, but you also have atoms from the asteroid belt or even outside of the solar system. And this leads me to think that maybe being from one place or the other, the place where we are from doesn't depend of a physical place, but rather it is a matter of time. Because in the end, everything is part of the universe. Because the Earth 5 billion years ago was also interstellar material, forming part of a nebula that little by little condensed in the form of what we now call the solar system. However, there are certain limits that we can establish. It's true that we're not from any country or planet or any solar system, but we can establish very clear limits. Because yes, the kiwis from New Zealand are made of atoms that were in the interstellar space many years ago, but these atoms had to be originated from somewhere. These atoms are from somewhere. And given that what characterizes atoms is that they remain unaltered since their creation, we could actually say that the place where these atoms originated is the place from which we are from. That's an easy answer, you'll say. In the Big Bang, of course. Right? Well, yes, but not the elements. In the Big Bang, only 3 of the 90 elements that you have on your body were formed. So there are 87 elements that were formed somewhere else. Let's see where. This periodic table could be perfectly understood as your space nationality table. As you can see, it is a normal periodic table that has as an addition the origin of each of the elements that make up you. Here you can see where you're from. Let's take a trip through the places of the universe where we were actually created. Through the places where we really are from. It all started with the first 3 elements of the periodic table, hydrogen, helium, and a little bit of lithium that were formed in the first 20 minutes after the Big Bang. Today, hydrogen represents 74% of all baryonic or normal matter, and helium at 24%. We only have the remaining 2%. In fact, the rest of the chemical elements are nothing more than 2% of the total. That doesn't mean that they are less important, so let's see where they come from. It's important to clarify that most of the elements with an atomic number greater than iron are formed in one of the most powerful events that occur in this universe: supernova explosions. There are many types of supernovae. That's why in the table the elements are not classified according to them. But in general terms, these are phenomena that occur at the end of the lives of stars that collapse under their own gravity, creating in the conditions that occur in their nuclei many of the heavier elements, from oxygen to rubidium. Just after their creation, these stellar monsters explode, creating the most violent and luminous explosions that we can observe in the universe. In this photograph of the galaxy NGC 4526, you can see how a supernova can be brighter than the billions of stars that are in the galaxy put together. But the elements lower than iron in atomic number are generally formed in stars of intermediate to high mass, before they explode in the form of supernovae. That is, during its life, the star consumes the hydrogen and helium that it has from the Big Bang, gradually forming layers with these new, heavier elements, such as the most abundant element in your body, oxygen, until iron is reached, at which time the star explodes because it cannot fuse the iron that is on its nucleus, and collapses, forming then the following elements after the iron. So all the oxygen in your body was released in an event like this. It's normal if you feel a little bit surprised, so let's see some calmer elements. The second most abundant element in your body is carbon, which is formed from explosions of low-mass stars, which are not supernovae because they do not have enough mass, so after they die, they just simply expel most of the elements to the vacuum of space, providing the galaxies with not only carbon, considered the king of the elements due to its affinity with the rest of the elements, but also with nitrogen, which is the fourth most abundant in your body. These explosions give birth to famous nebulae such as the Helids, called planetary nebulae, which tend to be very beautiful and very characteristic, so a good part of you was formed here. Beautiful, right? We still have left some less abundant elements in our body, but not for that less important, such as the pair boron and beryllium, some very rare elements that are formed in a phenomenon called cosmic ray spallation. Consists of a true cosmic billiard, when cosmic rays, highly energetic emissions that probably come from unknown, highly energetic events in the universe, collide with carbon atoms, for example, creating beryllium or boron atoms. That's why they are so rare. So the next time that you see boron, think that you're looking at billions of atoms, each of them being the result of a cosmic ray collision coming from the furthest corners of the universe, after traveling for millions of years, impacting by the most improbable of chances with a single carbon atom suspended in the already empty vacuum of space. And you have millions of them in your body. Don't tell me it's not fascinating. Those cosmic rays traveling such distances for so long, colliding with some atoms there, alone, to end up forming you. And we only have two more origins to reveal, one of them being white dwarfs. Important elements as copper and sulfur are formed in a peculiar type of supernova called 1A, which consists of the merge of a white dwarf with a part of another star of any other type, as long as it is not a neutron star. It's not a complete merge, because what the white dwarf does is gradually assimilate part of the other star, which spills its material in the white dwarf as if it were a black hole. And when the so-called critical mass is reached, the white dwarf explodes, releasing the elements into the vacuum. One example of a white dwarf is Sirius B, the companion of Sirius A, the brightest star in the sky after the sun. However, in their case, the explosion will not occur, since they are too far apart to merge. What will indeed happen is that one day our sun will end up being a white dwarf that will not have a partner with which to form a type 1A supernova. Because yes, we don't always keep it in mind, but our sun is nothing more than one of those stars that we see in the sky every night, only much closer. And we only have the heavy metals left, which are the heaviest elements. These elements are quite rare in your body, but many of them are still quite necessary. Although they're also formed in supernova explosions, in recent years studies have begun to be published that explain how a good part of them could have been formed in collisions of neutron stars, the most dense and small stars. These being able to have a radius of only 10 kilometers, but a mass twice that of the Sun. They have, as you can imagine, a very strong gravity, and that is because their density is 10 to the 17th kilograms per cubic meter. 1 cubic meter of a neutron star weighs the same as 2.5 billion Titanics. Only 1 meter. Neutron stars are the last step before forming a black hole. If they are too dense, they end up collapsing into one of these. And then there is no going back. And part of you was formed in that environment. Some of the atoms in your body were in one of the most extreme places in the universe. They were in an environment of enormous pressures. They were close to becoming a black hole. But they are with you because you're here. It's curious to think that of all the combinations of atoms that could have occurred in the universe, after all the necessary events to form the atoms, precisely the combination that was necessary for you to exist occurred. Supernovas, stars that almost became black holes, cosmic rays making highly improbable collisions after traveling billions of years, the Big Bang. All these elements have traveled through the cosmos to become part of the person who's watching this video. So you can feel important. But we're not just atoms. We need something else to exist. And that is energy. So we still need to know where a good part of us comes from. And with this, I want to clarify that matter is nothing more than a form of energy, but it's a form of energy that many years ago ceased to be simple energy and became a form of energy, matter. Now I'm going to focus on energy in its purest form, the energy that us humans use to survive that comes from the chemical bonds that exist in what we eat. Whether it's plant or animal food, we ingest molecules that would become biological batteries that our body is capable of decomposing to get their energy. Energy that both animals and plants and any other living being that you can imagine got from another place, either from another animal or plant or from a lamp in a greenhouse. So we could do the same analysis as before. Each country obtains its energy in a different way. In Iceland, a lot of food is produced in greenhouses with lamps lit with energy from geothermal generators that use heated water that comes from the depths of the earth. But in other countries, the energy is obtained, for example, from burning coal or directly from crop fields fed by the sun. Because with energy, it's very different than with the elements. All the energy that we obtain here on Earth either comes from its residual heat, from disintegration of radioactive elements, or from the sun, our star. But could we go back to the past in which all the energy had a common origin, as with the elements? Well, yes. And that origin is the Big Bang. All the energy present in the universe was formed in that instant. That energy that makes us what we are came from there. But you're not strictly from there. Because it's not that you are exactly that energy. It's not that you have constant energy. You simply use it. It flows. Remember that like the Earth, you are an open system. And each time this energy is used, it is spent and dissipates more in the cosmos. That's entropy. Sounds familiar? Just like the second law of thermodynamics says, the entropy, which is the usable energy of a closed system, always diminishes with time. And yes, I know that you're not an isolated system. That's why you constantly spend useful energy. But you know what? You're doing it by perpetuating the death of a system that is isolated. The universe, that little by little sees how its energy is spent, bringing it closer to the big freeze. The day when all the energy will be too dispersed to be or be part of something. So, in a way, with that incessant flow of energy that you are part of the slow death of the universe. So, instead of wondering where we come from, maybe we should ask ourselves, where are we going? May the small sacrifice of the universe not be in vain. Thank you very much for watching the video, and goodbye.